Welcome back. So one of the things we do a lot with the principle of conservation of momentum is study particle collisions. And I'm going to use collisions the same way we did last year when we were doing intro physics. And I'm going to talk about collisions as being any system where I have an initial state with a certain number of particles and a final state with the same with also a certain number of particles, and that thing is somehow closed, right? So that the initial state led to the final state without anything being inserted or taken away from the system. And so the example that I'm going to do first to show you how to do problems involving collisions in special relativity is to think about what happens when I have a particle that just explodes. Okay, now that's the classical picture, right? I have some firecracker that goes off and it breaks up into different parts. In particle physics, this might be a nuclei, right? Or a nucleus, and that nucleus decays into two different things. And what we're going to find out is that when I conserve form momentum, I actually get a lot of information out about that final state that comes purely from the kinematics associated with the different conservation laws that we have. So I have some large, say, nucleus or particle of mass m, and it's going to decay into two smaller particles, one of mass m1 and one of mass m2. And that final state, so in the initial state I can put it at rest, in the final state I can no longer put it at rest, and so I'm going to just call the final spatial momenta of m1 and m2 p1 and p2. So this p1 and p2 are the spatial components of the form momentum, right, which only in the non-relativistic limit correspond to the old-fashioned momentum. And what I want to know is, well, what's the final energy of one of these particles? Now, this can be a very important question, like say if you're doing radiation therapy and you're going to use some nuclear process to generate some sort of isotope or some sort of particle that you then want to use to treat a tumor, right? You need to know how much energy do those isotopes have when they leave this collision. And so a calculation like this could be very important if you're thinking about creating radiation doses to treat cancer. There are also other applications to this, but I want you to realize as we go into this calculation that the laws of special relativity, that the fundamental nature of matter and energy actually lead to really important things that we need to do things like to treat cancer. Okay, so here's the procedure when you see a problem of collisions in special relativity. First, and this is going to remind us of how we dealt with collisions before, you want to start by writing down all of the form momenta for your initial states and your final states. Once you have all of those form momenta, you're going to write down the conservation laws that correspond to each of the four conserved quantities, the three spatial components of the form momentum and the time component. Then there's a trick. Because I know about reference frames and invariants, it's actually useful to take the full expression for the conservation of form momentum, solve it for something you don't want, and then take the dot product of it with itself, and actually that turns out to be often a useful identity. And that basically is utilizing the fact that we have symmetries of the form momentum, that we have properties of the form momentum that help me to understand something about, say, the total magnitude of the form momentum. And then once I have all of those formulas, it's basically down to algebra. And I'm going to label step 3 as sort of advice, right? So when I have problems like this, when I have problems with lots of equations, some of which can be redundant, there's a certain art to solving those problems. I'm going to show you one way to do it for one problem, but the more problems you do, the better you will get at figuring out what strategies you have to come up with the equations that you're going to need. Okay. So let's start. The first thing we're going to do is label all of the form momenta and write down what we know. So in the initial state, I have one mass, capital M, and it's at rest, and so I can easily write down what the form momentum for that particle is. The final state's a little bit more complicated, and since I'm not going to restrict myself to the non-relativistic limit, I'm just going to call the energy of these two particles E1 and E2, and I'm going to call the spatial momenta P1 and P2, and I'm going to leave that in the vector part for now, and I'll only solve for the components of the form momentum if I have to. Okay? So the form momentum for particle 1 is E1 over C colon P1, and the form momentum for particle number 2 is E2 over C colon P2. Okay, step 2. write down all my 4 conservation laws. Well, the time one is easy. MC equals E1 over C plus E2 over C, right? That is going to give us the relationship between the time component of the initial momentum and the time components of the final momentum. And then I have all of the spatial parts, right? I have that 0, because there is no spatial momentum initially, is equal to P1 plus P2. And right from here, you can see that P1 is going to equal minus P2, that this collision always happens collinearly, right? So if I wanted to go further with this and calculate the components of the form momentum, it probably would be best for me to choose some axis and align the final state along that axis, although I don't necessarily have to do that now. Anyway, at this point, I now have 4 conservation laws, 1 from the time part and 3 from the spatial part, even though I'm writing those 3 as a vector equation. Now, step 3, again, is a piece of advice. Oftentimes, I can simplify the problem by taking the expression for conservation of form momentum and solving it for something that I don't want. Okay, and you'll see why. So in this case, full form momentum says Pm is equal to P1 plus P2. I'm interested in figuring out what is the energy of M1, what is E1. So I'm going to solve this expression for P2, okay? And then I take that expression for P2 and I dot it with itself. I take the 4 dot product of P2 with P2. The left-hand side is just the 4 dot product of P2, P2. And the right-hand side actually has 4 different terms, but 2 of them are the same, and so I can put it into 3 different terms. Now, I have 5 total equations, right? I have the 4 from the conservation laws and this 1 extra equation that I got from this dot product. Now I have to do algebra. So really what you do when you're sitting at home doing these problems is you stare at those equations and you start to plug some equations into each other, and you spend a lot of time manipulating that algebraic expression to see if you can come up with something that answers the question beautifully. Now, I'm doing this on the video, so I've already done that, right? And I know which equation to start with. But this is something that isn't obvious, right? It took me a while to play with the equations to find out what's the quickest way to get to this answer, so that way you'll actually watch the video. And so what I found was that I can get to the answer that I want actually by studying that equation that came from step 3, right? So this is the P2 dotted with P2. And the reason why that's so useful is if I look at all of those terms, many of these things are space-time invariants, right? If I have any particles for momentum, 4 dotted with itself, all I get out is mc squared. Right? And so it doesn't matter, the details of the explicit form of the form momentum doesn't matter for 3 of the 4 terms that I have written down. I have m2c squared on the left, and I have mc squared on the right, and m1c squared on the right? 3 of those terms are trivial just by choosing this interesting combination. The term that's left looks hard, but again, I can evaluate that in any reference frame I want, so why don't I evaluate it in the lab reference frame, where of course m is at rest and so only has a time component, and therefore the 4 dot product of Pm and P1 is just one number, right? It's mc E over C, which is just m times E1. And now you can see why I solved for something that I didn't want. Because when I put all of this back together, the only unknown left in this expression is E1, right? So if I know that I have some parent nucleus that breaks into these 2 other nuclei, I can actually find out what the energy of those 2 nuclei are just by knowing the masses of each one of the particles that are involved in that collision. And that's why we know so precisely, right? If we have some some uranium nucleus that ejects a neutron, right? I can actually calculate what the energy of that neutron is without having to experimentally measure it, because there's only one solution for the energy of that 2-body final state that conserves form momentum, right? And so now I'm actually done with the problem because I've answered the question and I didn't use all of the equations that I had, although in general I will need more than just this one equation. This is a pretty simple case. But it's best to stick to that strategy because generally when you do that, you always have enough equations to solve the algebra for what you want. And I want you to know that this really is an art. Okay, it looks easy when you're given the right equations and you're given the right process, but it actually takes a lot of practice to be comfortable enough with the equations to find out which ones you need for which problem. But once you learn it, or once you do it enough that you get used to it, you actually find yourself kind of playing magic, right? That you can take a very little piece of information, combine them with really important fundamental characteristics of space and time, and come up with extremely important results that, in this case, have life-saving applications.